Okay, now I think we can start with the seminar today. There is Llorenç, Serra, all of you know him. And he's going to talk about a very interesting problem. Well, from my point of view, it's a very interesting problem. He had yesterday on Pauli an interview about this topic, but today he's going to be a bit more technical on this. Well,
thank you very much, Rosa. Well, first, it's a pleasure being invited to give a talk at your home institution. I'll try not to be much more technical than the interview that Rosa has just mentioned. My subject today is a kind of hot topic in condensed matter, is this Majorana mode in semiconductor nanowires. These are my collaborators, Jongsu, Rosa, and Ramon Aguado from Madrid University, from Institute of Material Sciences. Let me first begin by mentioning a few experiments last year, in 2012, measuring conductance properties of semiconductor nanowires. The first is this experiment done in the group of Delft. I will refer to the experiments by the place where it has been done. The leader is Leo Kowenhofen. It was published in Science. This was the first measurement using the semiconductor nanowires and obtaining evidences of these peculiar properties we are going to discuss today. Other groups have subsequently measured and confirmed this behavior, obtaining the same physics. Let's say they have confirmed that the same physics is seen in Sweden, in Lund experiment, in the United States, in Indiana, and in Israel, the Weizmann Institute, and recently collaboration of Massachusetts, of the MIT, and Harvard, and Northwestern. All of them have confirmed this behavior we are going to discuss. I would also like to mention a very recent workshop on these properties that was held at the Kavli Institute of Theoretical Physics in the University of California in Santa Barbara. And especially I want to mention the talks that you can have access online and in this address. It was just last December, and I would especially mention or recommend the talk by Leo Kowenhofen, the leader of the first group. I have used some of the suggestions or even some pictures from this presentation. As happens in physics, many times in which a new result is obtained and is, let's say, explained to the public, some distortions are introduced or some gross exaggerations. This has happened also in Majorana, Majorana states in semiconductor wires. For instance, some headlines were mysterious particle found after decades of searching, or even more spectacular, Majorana fermions, the answer to life, the universe, and everything. So we are going to see what's behind this. The outline of my talk is this one. I have divided the talk in two main parts. I will spend most of the talk with the introduction, giving motivation, what is the reason to be interested in these states, this kind of physics, and I will give two motivations, two main reasons why this peculiar behavior have attracted so much interest. Then I will mention the physical scenario of a semiconductor nanowire. And in the last part, I will focus on more specific works, which are our contribution to this field. We started studying these things recently, just last year, so we are still learning about these systems. I will mention about the states of a finite nanowire, theoretical calculation, the transport through a nanowire coupled to normal leads, and also the problem of the semi-infinite nanowire. So let me begin with motivation number one. Is kind of, let's say, unexpected or surprising connection, I would say, which links nanoscience with particle physics. This is summarizing the words of Leopold in this workshop I was mentioning before as particle physics on a chip, on a small, on a micron size device like this one. This is a kind of artistic picture trying to give this message. Here you have the microstructure with these circuits, the chip, let's say, in which the measurements are done in nanoscience. And on top of this, you have a picture of a facility in Geneva, which is in the accelerator in CERN, the Large Hadron Collider. This size is, this system has a size of a few microns or several microns, while this system has a size of tens of kilometers in radius. This is this collider in which beams are accelerated and they are colliding. Surprisingly, both systems or properties from both systems have been seen to be related in these Majorana systems. The underlying idea is that in nanoscience we can tune the system properties, while in particle physics the experiments are observations of phenomena, while in nanoscience, let's say, the conditions of the physical systems can be tuned to observe the phenomena we want to see. Of course, this can be done to some extent. There is a spectacular difference between both types of approaches. In nanoscience, these are small scale experiments with small devices, with a few people. In particle physics, it's a large scale with big facilities and a lot of people. Let us begin to clarify this connection. Let us begin recalling the structure of elementary particle, let's say, the Dirac elementary particles and antiparticles in nature. Dirac suggested that we can have particles as excitations or states at positive energy, and we can also have opposite states, let's say antiparticles, which can be understood as holes in a field C. So we can associate a hole in a field C as the opposite of the electron, for instance. It would correspond to the electron and the positron. The electron is the particle, the positron is the antiparticle. They have completely mirror image electromagnetic properties. When they, let's say, collide, or when they coincide, particles and antiparticles can annihilate, normally in the form of photons. Photons carrying away the energy are emitted. This structure of particles and antiparticles suggested by Dirac is valid for all fermion elementary particles, constituents of matter, electrons and quarks, up and down quarks. These three particles are the, let's say, the elementary fermions. Then we can have composite particles by considering composite systems of several quarks, the proton and the neutron. Then by joining protons and electrons, we can have atoms and molecules, and then increasingly larger, let's say, pieces of matter or states of aggregates of matter. As the system evolves in this way, we may have, or we have, emergent properties appearing at different levels of condensed matter. These are the matter fermions, and we also have, of course, the antimatter fermions. Antimatter composed of positrons and the antiparticle of the elementary constituents. These are the elementary particles, which I just, let's say, flashed very fast. And Majorana particles is an idea that was hypothesized by Ettore Majorana back in 1937. He suggested that there could be another type of particles with the peculiar property that particle and antiparticle are the same thing. We may represent this as a quality of the operator creating and destroying this particle. Its particle and antiparticle are the same thing. These peculiar Majorana particles should have some properties, which are they should have zero energy, they should have no mass, no spin, no charge, so they have almost nothing, we can say. And perhaps this is why they have not been seen. They were suggested by Majorana, but no confirmation has been found that a Majorana particle, elementary particle in the sense I was saying before, has been seen. There was some controversy at some point that neutrinos could be a Majorana particle, but this is not yet resolved. So this remains then as a hypothesis which was not verified, not confirmed.
Zero energy, no mass. When you see something that has no energy, no mass.
Yes, maybe in this picture of elementary particles, I should say that energy and mass are equivalent in this language. So zero energy is actually zero mass.
A photon has zero mass, but has energy. Neutrino has zero mass, maybe, but has energy. Neutrinos have energy.
Here by energy I mean rest mass, energy, let's say. Mass, or let's say, yes, for elementary particles we should think of mass. We'll see that energy and mass can be different in these new citations. So Majorana particles should have no mass, no spin, and no charge. No spin and no charge because since it coincides with its mirror image, cannot have any charge or any spin. We can think of a Majorana particle as a peculiar particle or a peculiar system state which is half particle and half antiparticle at the same time. If we think of the operator of the usual creation operators for fermions, if we imagine that this creates, for instance, an electron and this creates a positron or annihilates an electron, we can think of a new operator formally, mathematically. So we can define this operator here as C dagger plus C. This would be a sum of creation of an electron and creation of hole. Or we can have this combination with the minus here and with the I here. This combination, these are purely mathematical constructs. And for most fermionic properties, we know that they have no deep physical meaning because the actual constituents are these fermion and antifermion. But in nanoscience, we can find a system in which these kind of particles, these kind of states, let's say, are the true eigenstates of the system. You can see that this combination here, they are self-adjoint. If you take the adjoint of this operator, it remains the same, and also in this because of the I in front. And this, as I said, this can happen in nanoscience. In these nanowires, semiconductor nanowires, can have states which are normal fermionic states, electron or post or hole, let's say in the bulk of the nanowire. But if you go to the tips or the edges of the nanowire, in some conditions at the edges of the nanowire, some states may appear which have this peculiar property of being their own anti-particle. To give you intuitive or simple picture, you can think of the states in the bulk of the nanowire as a glass being full of wine, then this is an electron state, let's say, or a glass being empty, then and this is a whole state, and these are the normal situation we are used to think of. But at the edges, we can have in some situations states which correspond to a glass which is half full. You can view this as a superposition of a full glass as an empty glass at the same time. And in this aspect, this is the Majorana property of the edge states that appear in the nanowire. What is the evidence of these peculiar states appear at the edges of the nanowire? This is done, as I said, in the Delft experiment, the first experiment that obtained these physics. This is done using indium antimonide nanowires, diameter about 100 nanometer. A nanowire is contacted to two electrodes, let's say one metal electrode, a gold electrode, and a superconductor electrode, an niobium alloy contact electrode. And then current is passed through the nanowire. Current electrons must come from the metal, let's say, go into the nanowire where we may have these peculiar edge states, and then go to the superconductor. What the experimentalists have measured is the current connected to a voltage difference between both electrodes. And they see these traces. Actually, this is the derivative of the intensity versus with respect to the gate voltage. And at zero bias, they see that a peak appears in the differential conductance. This peak is not present at very small magnetic field. So the first trace is for zero magnetic field. And at some magnetic field, this peak appears and remains there for some range of magnetic fields until it splits. So this is a robust peak that appears at zero bias. This is what we would think of a zero energy state, let's say. Then we have other features connected to the superconductor gap, which appear at finite bias. But the evidence is this peak, which remains from 0 to a few fractions of a Tesla. This is up to 0.5 Tesla here when it disappears. This peak at zero energy is not affected by a magnetic field, so it has no magnetic properties. Like a Majorana should not have any spin. This peak is not affected either by an electric field. Experimentalists have measured that the zero bias peak remains there when an electric field is applied. So it's electric field independent, and it has been obtained that this peak has some anisotropy with magnetic field, and this peak is present only when the superconductor is present in the experiment, let's say. So if you remove the superconductor, the peak disappears, and it has several features that theoreticians have suggested you should have for a Majorana type of state. So this was my first motivation. This zero bias peak, which is B independent, electron independent, all these are features that can be understood as physics of this Majorana type of state.
What do you mean by anisotropy? It's B independent?
Yes, that here a magnetic field is applied along some direction, this direction, and you obtain the zero bias peak. If you apply the magnetic field in a perpendicular direction, let's say, then this peak disappears. And as we will see later, theoretical models predict this type of anisotropies. So for theoretical models, let's say these are signatures or let's say evidences that this is a state of this type. So this was my first motivation. My second motivation is a connection of these Majorana states that appear at the edges. A connection with an application in quantum computers, let's say. this connection involves these three main properties. We can see that of the Majorana edge states have a property which is non-locality. We can view this property as a fact that if we use the inverse transformation, that we write the fermion state as the sum of two Majorana states, these two Majorana are located at different edges of the nanowire. So we can interpret this relation here like saying that a fermion is occupying or is having a state in which it is delocalized on the two edges at the same time. And this is saying that this fermion is delocalized in the nanowire. It has a non-locality property, let's say. This non-locality property gives protection against perturbations that, for instance, that only act on one edge. This kind of perturbation can give you decoherence, which is one of the main obstacles for a quantum computer. A quantum computer based on a localized particle, for instance, on the spin of the particle, one of the problems is that the spin of the particle does not remain forever. It decoheres because of coupling to the environment. While these delocalized type of states would be protected against local sources of decoherence. Majorana type of states, they have also the property of being non-Abelian anions, which is a property connected to the statistics with the exchange of two particles. And this gives a possibility, this has been suggested as the basis of a so-called topological quantum computer. A quantum computer based on states which are delocalized on the tips of the wire. If we remember the change property of two normal fermions, two electrons, for instance, Pauli principle tells us that there is a minus sign whenever you exchange two fermions. This tells you that by exchanging electrons, let's say the global state only changes by a plus or a minus in general. But with non-Abelian anions, this is different, because when you exchange these states, the global, whenever you exchange two of these states, the global system of many of these particles changes in a non-trivial way. The exchange of Majoranas depends on the braid, let's say, on the way you do this exchange. And this is similar to the rotation of vortices you may have in two dimensions. For instance, in a superconductor, vortices in currents may appear localized to impurities in the superconductor. And when you exchange two vortices, one has normally to introduce a cut in the faces around one vortex. And when you move one vortex around another vortex, whenever this branch cut is crossed, this introduces some non-trivial jump in the face of the system. So this is telling you that if you move vortices around one another, it depends how you move them. The idea is the same for Majoranas. In a 1D wire, if we think of the two Majoranas on the edges, it's difficult to imagine how to exchange these two Majoranas, because at some point they would have to cross each other and they would annihilate. But it has been suggested that in networks of nanowires, this could be obtained. For instance, this is suggested by these authors. And here, if we think that this is a nanowire with two edge Majoranas, here another two Majoranas, and this is another nanowire in a normal state. So when we draw with this blue color, when the nanowire, let's say, is in a fermionic state, and in orange when it is in a Majorana state. what is the way, how can we change Majoranas number 1 and number 2? So if by using gates, let's say the physics, or let's say the connection of these two nodes of the network can be changed to a fermionic normal state, then this Majorana state, which was at the edge of this wire, will jump to this state, and we can view this as a new wire with the state, with the Majorana at the edge number 2. Then moving again this blue thing in a clockwise manner, anti-clockwise manner, sorry, then the Majorana which was sitting here will jump to the other edge, and we obtain a change of the two Majoranas by controlling the state of other parts of the system. This blue line here would be a situation in which we have the presence of Majorana or a normal fermionic state. So this is, we can call it clockwise braiding, because Majorana number 2 jumps here, Majorana number 1 jumps here. If you move the other way around, the final state is different, and the difference is more than just sign. There is non-trivial change. You can think of manipulation of Majoranas in arrays using this type of gate-controlled coupling of the nodes of the network. So for instance, here with this orange, we think that we can represent a state in which we have two Majoranas at the edges of this nanowire. Then by changing the coupling of these two nodes, we can effectively change the situation of the two edge Majoranas. Or we can also think of the exchange between, for instance, one Majorana at the edge of this nanowire and this Majorana at the edge of the other nanowire. By changing the coupling of these two nodes, then this Majorana may jump here and this may jump here. So we can have, let's say, we can move around the edge states. This can be the basis of topological quantum computers. As I mentioned, is not the fact that how does the system evolve when you move Majoranas around depends on the type of motion, can be the basis of topological quantum computing. The basis is that when you exchange two anyons, two Majorana states, you can have one state which we can represent this way, in which the green line is on top of the blue line, or we can have the counterclockwise exchange in which the blue line is on top of the green line. And both states have a non-trivial difference. They can be, let's say, the basis for quantum game. And a calculation can be just a sequence of changes in time. A computation can be the result of braiding the Majoranas in some well-defined sequence of steps. For instance, here, first changing in a clockwise manner this nanowire, this Majorana state with this Majorana state, then changing these two also in a clockwise or anti-clockwise manner, and at the end of the sequence of changes, we find a final state which may be the result of the quantum computation. And the idea is that this sequence of process, this operation principle, is immune or is not affected by decoherence in a local scale, by, let's say, perturbation acting locally, because these are states which are spread on the system. So this is the second motivation, topological quantum computation.
So one question is, normally for quantum computation you need decoherence, but you also need to control the phase. So if you now shift Majorana states along here, you swap several states. Don't they need to have a control or at least a fixed phase relationship between each other?
Yes, with these exchanges you control both things, the phase and...
But how do you control the phase if you cannot access it?
How do you control the phase? No, with this braiding operation, of course, this is a suggestion. This has not been realized. This is a hypothesis that if you could control precisely this braiding operation, this clockwise swap and this anti-clockwise swap, this would be the basis of a robust operation principle, because you would control the change of the quantum state of both things, and it will not be affected by local perturbations.
What is the swap? The swap between two Majorana states, or only the swapping of the location of one?
Can be, for instance, as we mentioned here, you have Majorana state number 1, Majorana state number 2. By doing this sequence of steps, you exchange this Majorana with this Majorana, 2-1. Only the Majorana at one edge. And the non-trivial property is that the Majoranas are like non-local states of fermion, and you are exchanging just half of the fermion.
But you need, if you change the two Majorana states, which are building one fermion, and you switch one Majorana to the other one to consider a new fermion, don't they need to have a controlled phase relation between each other? Otherwise, the superposition will change.
Yes, you need to control that, and it's not equivalent to exchange two Majoranas on the same wire with one Majorana of one wire with another Majorana of the other wire. This is highly non-trivial difference, so they can be completely different. But the idea is that the phases are controlled in this braiding operation, and it depends on the way you do the sequence of braidings. But this is, I just want to give you the idea or one of the motivations on the interest in this Majorana. This is, let's say, a hypothesis. It has not been verified yet, and people is trying to first understand if Majoranas first exist, and later how to do this experimentally. So the physical scenario I want to give you for a semiconductor nanowire. How can these states appearing at the edges of the nanowire be produced? So for the emergence of Majorana physics in a semiconductor nanowire, we need three ingredients. One ingredient is the superconductivity or pairing, which is induced by a nearby superconductor. A nearby superconductor is inducing the electron-hole symmetry and the pairing in the way of superconductor. So this gives you basically this scenario that you have electron state, hole states at negative energy, and there is the superconductor gap. Then if you add a magnetic field, a Zeeman field, then we expect that some states may go down in magnetic field if this parameter represents the magnetic field. We have one state going down, others would go up, which we don't draw here. For whole states, some state will go up and others will go down. For some value of the magnetic field, we may expect that they coincide or they cross around zero energy. In this way, let's say the Zeeman field can compensate to some extent the superconductor gap. Still, we would only have accidental crossings here. While for a Majorana state, we expect it to be robust, let's say independent of the precise value of the magnetic field. This is obtained by means of the Rashba spin-orbit interaction. Theoretically, the Rashba spin-orbit interaction is introducing helicity, it's introducing a coupling of the spin with the direction of motion, and it's introducing, let's say, anti-crossings here. These states no longer cross, but they anti-cross. As a result, there is an effective repulsion between these levels, and one state appears which is, let's say, P at zero energy. And this is the manifestation of the zero energy state, which we can understand as a Majorana-like state, which is, let's say, the same of its antiparticle. This would be particle state, this would be antiparticle state, and this state lying precisely at zero energy coincides with its antiparticle and will be this Majorana state. So this was...
Why this only would happen in a wire and not in a quantum well or in a quantum dot.
Yeah, this does not only happen in a wire. Let's say this is one mechanism in which these states can appear. But in experiment, there are other proposals of appearance of zero energy states in cold atoms or in vortices in superconductors. There are other systems. So a nanowire is just one example in which by controlling these three mechanisms, you can induce the appearance of this type of states.
But could you do the same in a quantum well?
In a quantum well, I would say it's very similar to a nanowire in quantum well. So you probably would need also superconductor and Zeeman field.
No, all I'm trying to understand is if the one-dimensional thing is essential or not. By wire, I mean that it is one dimension, right?
Right.
And I'm trying to understand if dimension here plays any important role or not.
I would say yes, because it's a peculiar property of this state that it appears at the edges. So if you think of a bulk quantum well, then these are states that for that you need interfaces. So they appear pinned at the interface. So in an extended system, you do not obtain this zero energy state. A nanowire is an example in which you can induce this type of state at the two tips. But in a quantum well, probably you would have these states around impurities. You have some kind of impurity, you can have a zero energy state localized on the impurity.
And the quantum dot?
And probably also in a quantum dot. This is just a suggestion or which has been realized in experiment. So these were my two motivations. And now I want to go to this a bit more specific part, which is the models or the specific things we have addressed. First thing we have looked at is a description of the edge states or tip states that appear in a two-dimensional nanowire using this model which I represent here. We especially wanted to focus on how robust is the emergence of the zero energy states with respect to the length of the system and with respect to the direction of the field. So if you have the field exactly along the x direction or you slightly tilt it a little bit out of the x direction, how does the emergence of the zero energy state changes? This is the model. We use this representation.
The geometry is a two-dimensional nanowire.
Yeah,
Lx is larger than Ly?
Right. Lx is much larger than Ly. As we will see, and maybe this answers the question Matsi posed before. For the emergence of the edge state, you need Lx much larger than Ly. Otherwise, you don't see the formation of these zero energy states. So we assume this 2D geometry, Lx, Ly. We use the Bogoliubov-Dejean description of the states. So we just represent kinetic energy. This is the confinement to this red rectangle. Mu is the chemical potential, and we represent by tau operators the isospeed. Let's say the electron or hole degree of freedom. This is the kinetic energy. Then we have the Zeeman term with normal spin, sigma vector. Then we have the pairing parameter and the Rashba term, which is coupling Px, the momentum along x with the spin along y, minus the momentum along y with the spin along x, as you can see here. This term here, we call it Rashba mid-sync, because if you think of a rather long system this Py is the transverse momentum, and normally when you have, imagine for instance you have harmonic confinement along y, then Py would be connecting adjacent states in the transverse direction. So this would be coupling the states, different transverse states.
So by spin here, you mean intrinsic spin, there is no orbital angular momentum.
Here, when the magnetic field is in the plane, well, orbital angular momentum. With that, we have linear momentum, Px and Py. Yeah, we have motion here. When you tilt the magnetic field a little bit in the vertical direction, orbital currents can appear in the plane. So this is the result we obtained by numerically solving that model as a function of the Zeeman parameter. These are the eigenvalues, and as in the sketch I was showing before, we have some eigenvalues at positive energy, some at negative energy. There is a gap. Here we would have more eigenvalues, which we don't draw, and here we will have more eigenvalues. We just draw the first few states. When we increase the Zeeman parameter for a magnetic field along x direction, we see that there is a collapse of the states and the zero mode appears. We can understand this as the formation of the Majorana coming from the first transverse state. This is the Majorana from the second transverse state that would be present with the first and second at the same time. Then we have first, second, and third. So subsequent Majoranas would be appearing as you increase the Zeeman energy. If we take this eigenvalue here and we draw the space, the spatial distribution, we see that indeed it is an H mode. This is the first. Here we have two zero modes. This is the first one, this is the second one. The second one has one node here in the middle. So this is really edge states. As you see, when we increase the magnetic field beyond a certain value, we begin to see these oscillations. Actually, this oscillation is also present here, but here we don't see because it's very small. If we make the system shorter, then we have a larger oscillation here. So this is what we call the finite size effect. If the aspect ratio of the system is such that it is not long enough, then the state is not really at zero energy, but is oscillating around zero energy. So the Majorana character is not well developed. The longer the system, the more developed you have this zero energy state. Those were the results without Rashba mixing. When we include Rashba mixing, we have again the formation of a zero energy state, but in the region where we would expect the coexistence of two Majoranas here, we see that there is a repulsion between them. So two Majoranas would not really coexist because there is a repulsion due to the Rashba mixing. If you increase more the magnetic field, then we enter this region in which it's not clear to say whether there is a zero mode clearly separated from the rest of the mode, as happens here, or it's just a quasi-continuum spectrum, like happens here. This is for a partial Rashba mixing, which has been artificially reduced, and this is for full Rashba mixing, where we see again this gap here. If we draw here the first three eigenvalues around this region, we see that it does not have a clear edge character. So in order to have a clear localization at the edges, we need a scenario like this, where there is a zero mode with a gap to the next mode, clearly separated. As I told you, we also looked at the influence of magnetic orbital effects. If we tilt a little bit the magnetic field, then the vertical component will induce the appearance of orbital currents, and Majoranas are not robust with these orbital currents. So if this is, we draw here the energy of the lowest state as a function of the tilting angle, and we see that the state is at zero energy, but when you increase the angle, just for 1.5 degree, 2.5 degrees, there is a significant deviation from zero energy. So the orbital currents remove the state from zero energy. And also the gap to the next state is reduced when the field is tilted. Just by 2 degrees, for instance, is enough to remove the state from zero energy. So here we have seen that there are instabilities in two-dimensional finite nanowires with finite size effects. So the system should be long enough in order that this oscillation is really quenched at zero energy. And the magnetic field should be in plane. Just a slight tilting is enough to remove the state from zero energy. We are at present repeating this calculation for cylindric geometries, using a cylindric nanowire to see how is the behavior. So the next topic I wanted to mention.
When you say instability, you mean that they disappear?
Yeah, I mean, for Majorana, it should be zero energy mode. When it becomes a finite energy, it's a normal fermionic state. And when I say instability, I refer to this behavior here. That the state
Something that destroys the Majorana.
destroys the Majorana state. So it's not really on the edges of the system. Yes?
So your statement about decoherence being not sensitive to decoherence was regarding non-localized structure, so one that's already present.
Yes.
Okay, so but
So it should be at exactly zero. So this robustness against decoherence would require a real zero energy here, as much close to zero as possible.
So the Rashba mixing is a typical sort of decoherence in semiconductors, no?
Yes, it gives you randomization of the spin. If you have a well-developed spin, after some time this spin is...
so basically that means that the creation of the state itself is sensitive to decoherence, but once it's created, there will be no local dephase.
No, we see that Rashba mixing is dramatic, let's say, for two Majoranas coexisting, but not for one. One is still robust, let's say. Rashba mixing is not affecting one Majorana, but is affecting this region here. But we have, for the moment, just trying to understand the physics. So we have not really gone into the implication for decoherence or application in topological quantum computation.
Move back one more. So the lower plot is one Majorana.
Yeah. So this is the eigenstate of the Hamiltonian here, the first one.
One Majorana is one electron and one hole. It's a special
You can do
configuration.
like that, yes. So this is a state at zero energy. Electrons are states at positive energy, holes are a state at negative energy. So this is a state at really zero energy. So it's not it's one thing or the other, or the let's say a mixture of the two things at the same time.
But then there must be more. It's a quasi-particle, right? So it's
an
an electronic hole and what? What constitutes the Majorana particle as a quasi-particle?
No, it's this peculiar state which is not electron, not hole, but the two things at the same time.
There must be more to it than just an electron and a hole, right? Via interaction.
Well, it's an electron and a hole in this system, which is a condensed matter system. It's not one elementary electron and one elementary hole. It's a superposition of electron and hole in this already many-body system, which is the semiconductor. So in this sense, it's a collective effect of the whole semiconductor. I don't know if this is what you... So maybe more rapidly I can mention about other application. Next thing we have studied is the transport in Majorana nanowires. If we consider Majorana nanowire again in 2D, and then we consider the coupling to leads, to normal leads, let's say, then we can have the passing through of states, of electrons, of holes. We represent this in a model of parameters which are position dependent. We introduce this x-axis And then, for instance, we think of the Rashba parameter, which is 0 here. Here it takes the finite value and then 0 again. Or the superconductivity parameter, which is 0, finite value 0. Or we also introduce the presence of barriers here at the edges of, at the interfaces between the normal contact and the nanowire. Here I give you the one picture which I took from this recent workshop of the Pauli Institute to show you that this type of experiments are done at present in the Delft group, where they precisely have two normal contacts, the nanowire and the superconductor contact, which is inducing here the superconductivity by proximity. We expect here the two Majoranas formed at interfaces, and this will modify the electrical conductance properties. Well, we have used the coupled channel model. We introduced as a basis, let's say, the transverse modes along Y, and then the spinor wave functions in spin and isospin, and channel amplitude. This psi represents the amplitude of the wave function in a given transverse mode, given spin, given isospin. We can think of the transmission probabilities from contact I to contact I prime, I meaning 1 or 2. For instance, transmission from 1 to 2, from one type of particle, S tau is the isospin, electron or hole, S prime tau is electron or hole. The linear conductance, it's given by this expression, the probability of transmission from 1 to 2, let's say from electron type to electron type, plus the probability of transmission from 1 to 1, then it is reflection, 1 to 1, and a change of particle type. This is called Andreev reflection. This is an electron which is reflected back as a hole, or a hole which is reflected back as an electron. We can do the calculation of the transmission of the linear conductance as a function of the Zeeman parameter for B along X or for B along Y, and we see that there are dramatic differences of the conductance properties. For B along X, the magnetic field is parallel to the nanowire, and then we see that Andreev reflection, here represented in red is Andreev reflection, green is normal transmission. Andreev reflection is suddenly switched to a value 1 in conductance in the presence of the Majorana. If the Majorana is not present for B along Y, we see oscillation here, spikes in the conductance, and we don't find this sharp transition. There is also a difference when we enter this region in which the two Majoranas would repel each other. In this case, the linear conductance should decrease to 0 at some magnetic field, while for B along Y, we see again the formation of these spikes. So these are predictions, let's say, of the different conductance properties for B along X or for B along Y. We also find the zero bias anomaly. So there is a peak in linear conductance, in differential linear conductance at zero bias in this region when there is the Majorana, that goes to a dip when the linear conductance decreases, which is what they see experimentally. So the third aspect I will just mention in 2 minutes is the description of the semi-infinite system. So in these first two examples I have mentioned, we have described finite systems, either an isolated finite system or a finite system which is coupled to the normal leads. Another approach may consist in trying to describe the states of the semi-infinite system. By construction, we may assume that the system is semi-infinite. So we have here interface, and it extends from x0, from this value to infinity. In this sense, the description of the states in the semi-infinite system can be done using the idea of the complex band structure. The complex band structure is the description of the states as waves, but waves with a complex wave number. For normal waves, let's say Bloch waves, we have the amplitude is kept constant. As the particle propagates, the amplitude remains the same. This is a propagating state. We may have other state called Shockley state, in which the amplitude decreases as you go away from the interface. These are Shockley states. In this language of Bloch and Shockley states of crystals, of solid state physics, we may simply say that a Majorana is just a Shockley state of a wire. So we can describe the complex state. I don't think I have time to go into the details of this part. So maybe I just skip this. We have done in 1D and in 2D. And for instance, in this, with this complex wave description, you can find what is the distribution of the density for the Majorana in 2D. If you think this is this 2D wire extends to infinity, then close to the edge, which is here, we see the formation of these localized edge states. So with this, I come to my conclusions, which are very general. First, I would like to mention is that Majorana physics with nanowire is in its infancy. We are still trying to understand if they really exist, and we can reproduce these properties. It looks like, yes, different experimental groups have confirmed this kind of physics. This is an example, or this is a way to realize the physics which was envisioned by Ettore Majorana in elementary particle physics. But of course, this is now realized in a very different scenario. These states might allow us implementing quantum computing if we can really control the way we exchange Majoranas and how this state changes when by braiding the Majoranas. And in general, we need to understand better these states. So with this, I end, and I thank you for your attention.
Questions first from the students. We have top priority for making questions. We had already some questions. If not, then this opportunity is open to everyone. Okay.
So it's my understanding that Majorana states are solutions of the Dirac equation, or I will state the Dirac equation with zero energy.
Yes, for elementary particles.
For elementary particles.
Yes, but it must be at zero energy. This is why I said these are zero mass particles. You would say.
Okay, but there are solutions of the Dirac equation. Like here, you are solving Schrödinger equation.
In the presence of superconductivity, which we treat as the Bogoliubov-de equation, which is very similar to the Dirac.
So it effectively is like a Dirac equation.
Right. This Bogoliubov-de formalism that you have positive energy solution, negative energy solutions, and mixing within it. So effectively, it's like a Dirac equation.
I'm lost in many places, but the Majorana thing is a composite of electron hole or a pair of electrons and a pair of holes. I mean, I am the presence of the superconductor makes me. So what is the gap is between a state, the couple state of two electrons, between this and the corresponding hole. Is this the case? I mean, it's a two-body thing, it's a four-body thing, or what is this? How is the pairing of the electrons entering into the play?
Yes, the pairing is essential, let's say, because it must introduce this mirror symmetry between positive energy and negative energy. For that, you need a system in which you can access different type of states. And this is possible in a superconductor, where you have electrons and holes. And in this sense, it is essential. In the description of the Bob-de Jene is a one-body term, let's say.
But you have the in the kinetic energy, the mass is twice the mass of the electrons.
In the kinetic energy, no, the mass is the effective mass. So let's say these models, these are a way to infer the physics of the Majorana states, taking as a starting point a model of fermions, of normal fermions, let's say. So if you take a model of normal fermions, in which you introduce superconductivity, Zeeman field, and Rashba, this model leads you to the emergence of a zero energy state, which has the peculiar properties of the Majoranas. It's just a way, let's say, to from the description of fermions that we believe we know to some extent, describing the physics of this system, appears the physics of the Majoranas.
Okay.
So in this sense, the Majorana you can view as a superposition at zero energy of electron and hole state.
I mean, the wire there is no real superconductivity. So you use the model of the superconductor, but the electrons are not in the superconducting state.
No, yes, I think it is. The superconductor is in proximity to the semiconductor, so it's inducing really the coupling of pairs.
Particles. So these are excitations.
And the
above
Cooper pairs
ground
are
state
also, quasi-particles, so you understand the play between them.
So you have the ground state that are the Cooper pairs, and then you have excitations. So these excitations are formed by electrons and holes, and these are the Majorana.
Okay.
So they are indeed excitations above the ground state. Yes, of the.
But you can use the pairs in the superconductor that they tunnel into the semiconductor, in which you have this new interaction, which are the Rashba and the Zeeman field, and then they are modified in this peculiar way.
I don't know if this is nonsense or perhaps or not. Coming back to your first transparencies of gamma equal gamma dagger, I mean, can we understand this Majorana thing as a mechanism of symmetry restoring?
Of symmetry restoring.
Symmetry breaking, what you are doing is restoring the symmetry, right?
Yeah, probably you can interpret in this language, but I am not familiar with that. So
I have no idea if this has been discussed or not in the context of what symmetry breaking is about. But
there are symmetries.
My first idea when I see that is, well, that the idea is a mechanism of symmetry restoring.
Could be, but I would think that the external fields you need here, they are actually against these symmetries. No? So you have an external ambiguity field, and you also need this Rashba interaction.
Yeah, but the consequence of that is that you find a state in which you restore the symmetry.
Yeah, it probably can be reformulated or understood in this sense of the kind of symmetry restoration.
Questions?